Hi there and welcome back. I hope that you guys had a lot of fun in collecting the EMG data, and I specifically hope that my video could help you understand how to use the microcontroller and the EMG board to collect and save the data on your computer. Today we want to talk a little bit about how we can analyze the data and actually look at the magnitude and the frequency of these EMG data. Before we do this, there is one thing that I would like to talk about before. So I'm a person that always tries to take feedback from other people, because I think if you're doing something and you ask for feedback, you might get some good feedback. And if you use this feedback, and I've said it about 100 times, if you use this feedback, then you can better in what you're actually doing. So I also asked people about feedback about my YouTube videos, and obviously I've gotten some cool help. And one of the feedbacks that I'm specifically trying to make better now is that I am, what this person said, too Austrian and not very fun. So I don't know if you guys have ever been sitting in front of a computer and talk about what you're doing and also trying to be funny when there is no person sitting on the other side kind of like laughing about your jokes or even just smiling or whatever. Believe me, it is incredibly boring talking to the computer the whole day. So I've talked to a few YouTube people, and there is one suggestion that I really enjoy, and I'm gonna try this today, and let's see, maybe I'm gonna get a more funny person. So what I'm gonna do is I'm gonna take a video here, and I will put this into either this side or this side, I'm not very sure, so that you can see what I'm doing. I hope that now I can finally feel like I'm talking to a person, and maybe it will make me more relaxed and more funny. So let me know if it worked or not. It's hard for me to judge. And I guess let's start with the actual reason why we're here, namely talking about Python. So just a little bit of a summary what we're going to do today. We will mainly talk about how we can import the data, how the data looks like, and then we have to filter the data because there is a lot of signal interference in our data coming from cable movements or other interferences that we have talked about in the labs before. So we need to filter the data. Then we need to do something that is called rectifying the data. I'll explain to you guys later what that means. And then we also need to, or we will also do an envelope, which will show us how the magnitude for each time frame of the muscle activation looks like. But before we start this, let me share my screen, and let's talk about that in a bit. Before we start with anything, let's first have a look at the data sets. As we talked about in the last video and also in the lab manual, we had to do 3 different experiments, and each having 3 different measurements. The first experiment was the MVC data collection, meaning that that you guys had to contract your biceps as hard as possible, and you collected 3 different data sets for this. Then you guys did 3 different weights. So you guys held a weight for a few seconds, stopped the data collection, saved the data, did it again with a different weight and again with different weight. And then lastly, we did the fatigue experiment, where we again contracted the muscle as hard as possible, and we did that 3 times as well, okay? So these are the 9 data sets that you will need, as well as the lab 3 function for our code as well. But before we will start actually importing anything, let's first have a look at the data itself. And this is really important, and I really want to give you guys the tip of always, when you want to import a data, first understand the data before you do it. Like even if in my code I'm showing you that, like, for example, like let's say for here, for example, there is a comma separator. So there is the first number is the EMG, the second number is the time, and then in between I have a comma, okay? This is how the example data looks like on GitHub, and also how my data looks like. But your data was collected with the new Arduino code, and this doesn't use the comma. This actually uses a space separator, like you can see here, okay? So always understand your data, and when you want to import it, think about how the data looks like. In my case, I have a comma separator, so I will have to import it with the comma separator, and you'll see that in a minute, okay? Yours will probably have a space separator like we did with in the ECG lab, meaning that you have to use the slash and then the T. But yeah, you should know what I mean by now. So let's first import the pandas library now. I'm going to show you how we import some of the data here. First, use the pandas library here. We have, I'm just copying and pasting here because it's a little bit faster. We have the first column being the EMG data, the second column being the time data. And then let's now just have a look at how the first EMG data set looks like, okay? So I wanna import, I'm gonna import it with the pandas function read CSV. I'm gonna import MVC1.text, MVC1.text, okay? And as a separator, I am using the comma. If you guys don't have a comma but a space, then this is what you guys have to use, okay? That is really important. Please think about it. Use the /t and not the comma if you have a space. Then we call the two columns, we call them EMG and T. And I'm also deleting 50 rows in the beginning and 50 rows in the end of the data set, just because like you saw here before, what you saw here before, which one did I open? I can't remember. No, wasn't it? Maybe it was the weight one. Yeah, like here, the first row is not perfect, and then sometimes it's like 1-2 rows aren't perfect, so I usually delete a few. And 50 rows in our case is almost nothing, right? Because we have 1,000 hertz, so we have 1,000 data points per second, so it's way less than a second. Anyways, so if I just run this now, let's also maybe delete all my variables first, that everything makes sense. Reset, yes. Okay, so if I run this now, I have a variable called I am back. So it turns out that you cannot, and I have no idea why, I'm also not going to look about this for now, but you cannot, like here, create a variable with capital letters. So if I try to run this here, run current line, that does not work, okay? That was new to me. So, but if you do this here, you just do like the non-capital letters, then you'll actually get the variable which I wanted to show you guys. So now what we have is the first column is the EMG data, and the second column is the time data, finally. Okay, now we can plot the data, just have a look at how it looks like. For this, we also need the matplotlib pyplot library. Let me get that in here, okay. To run this now, there we go. So what we can see here now is that this is the part where I contracted my bicep, where I did the MVC, and here I was just doing nothing or almost nothing, and here as well. Something important to mention here, if you move in, zoom in here, you can actually see that the steps here are really big. So this is an obvious sign for not having a lot of resolution, not having high resolution. We talked about this in the last video, and I also mentioned this in the lab manual. So that's one of the let's say problems that we're having with the EMG board. It works well, but one of the limitations, that's the word that I was looking for, one of the limitations here is that the resolution is not very high because it sends out a very that the difference in voltage is very small. Even though we could measure from 0 to 5 volt, it's just measuring somewhere between, I can't remember exactly, 1.6 and 1.7 volts or so. So then the resolution gets really, really low. So that's where we could get an amplifier or something like that to amplify the signal, to have a bigger signal and a bigger range again. But we don't have something like this in our kit, so that's what we will work with. And that's why we also use the analog reference pin last time in the last video. But here you can obviously see that it's not the perfect signal yet. But that's what we have to work with now. Anyway, so that's how our data looks like. Let's now actually start with the actual data import because I wrote a function for this that I would like to show you guys. But here, that's how you could just import it and have a look at each individual file. Let's delete this here. And then we're gonna use a function from the lab3 functions library. So let's import that one. Import lab3 functions as, let's call it L3F to keep it same like always. And then we're gonna use a function from this library, which is called import data. And what this function basically is doing, it imports all 3 MVC measurements and puts them together into one data set. So on the plot, it will then look like you did all 3 of them together. It does the same for the weights, and it does the same for the fatigue. One thing is really important here is that if you will save the data in the working directory, because the function will just look in the working directory where you're looking right now, so it does not have any path or something like this. And also the data sets need to be called exactly like I called them here. So they need to be exactly spelled like I did. So fatigue 1, 2, 3, sorry for that, MVC 1, 2, 3, and weight 1, 2, 3. It needs to be like that, okay? And if we then import the data, okay. Import the data. So now we have a fatigue set, we have an MVC set, and we have a weight set, okay? So let's just have a look at the weights first. There we go. Let's see how that looks like. There we go. So you can see how my first weight was not as heavy as the second one or the third one. So you can see already now a big difference in the magnitude here. Even though, and again, our resolution is really, really bad, and here it's even worse because when we're not using as much weight, we're not having as much muscle activity, meaning the range of our EMG is even lower than with the EMG than with the MVC before. So this is yeah, not very good. But again, that's what we have to work with right now, and we will hopefully find a solution for that soon to work to make that maybe a little bit better soon or in the next semesters or something like this. I will update you guys. One thing that I forgot to mention is that with this import data function, the only thing that you need to give the function is the separator. So again, for me, since my data has a comma in between, I'm sending the comma. If you guys have a space in between the time and the EMG, you would send this here to the function. Let's now talk about how we can pre-analyze the data that we have just imported into Python. For this, I found a very cool website with a really good tutorial on how to filter the data, why to filter it in a certain way, and what rectifying is, and so on. The website is called Scientifically Sound, and I'll show that to you guys. They have a full tutorial on, first of all, in part 1, so we started part 3, but what they did in part 1, they created artificial EMG signal because we collected this, we don't need to do it. In the second part, they then talk about why some EMG values are offset from 0 and why we have noise and so on. So the offset is something we also have in our data. If we, for example, look now at the plot here, we have an offset of 315, something like this, and we want to have an offset of about, like, we want to be at 0. This is just like the reason for this offset might be different reasons, but in our case, it is because of the EMG board that we're using, because that's the way how it outputs the data. It's not around 0, it is something higher, and in our case, yeah, that's around 315. And then in part 3, they actually start to explain how we can remove this offset, how we can filter the data. So for filtering, we want to be somewhere in between, like, so because of the cable shaking and some other signal interferences we have talked about in lab 2 already, we get some, we get some frequencies in the signal that we don't want to. And because we know that our muscles usually operate between 20 and 450 Hertz, we're gonna create a filter that filters out everything that is under 20 Hertz and everything that is 450 Hertz. And then afterwards, we're gonna rectify the signal. So now we can actually talk about what I mean when I say rectification. So when you have the data at zero offset, then and you wanna see how the muscle contracts and how the muscle activates, then you usually want to calculate the mean of the muscle activation. So then what you want to see is that it goes here almost at zero, and then it goes up because here we're contracting our muscle, and here it goes down again. But since our muscle has activations in the positive and in the negative voltage area, the mean will always be zero, and we will not get the data we want to have to. So when we rectify it, we just take the absolute value. So like we now take the minus and make it plus. We take the absolute values of this, and then we just have the positive values. Meaning now, if we now take the mean, it would actually go up here. And we can see where the muscle is activated and where it is not activated. So the cool thing with this website is I'm, by the way, also gonna put a link into the description of this video. I would really recommend you opening this now, because you will probably want to copy and paste a lot of those things, because most of the code that is written here is we can almost use directly. So I'm gonna put this away now, but again, I suggest you opening it now and maybe even reading a little bit over it so that you understand what's actually going on. You might have, or you probably learned most of this already in our lectures, but it will definitely make sense to directly understand it with this data here. So for this, what I'm gonna do now is I'm gonna start a new functions library, and I'm gonna create a function for every single thing that we're doing. So for example, for the removing the mean, I'm gonna make its own function. For the filtering, I'm gonna make its own function. The reason why I'll do is because later you guys wanna do this, the next few steps that we're doing, you wanna do this with the fatigue data, you wanna do this with the MVC data, you also wanna do it with the weight data. So if you have a pre-written function, you can always do it for all the data that you want to. I'm just gonna show you guys how it works with, let's say, the weights, because yeah, that's the most beautiful to show, because you can see the different activations in the end. So if you wanna start a new library, we have to start a new file. And then we can save this. Let's save it as, and we save it in the same working directory. Let's save it as EMG functions. I think that's a good name. So now EMG functions is saved here. And then our first step, as we talked about before here, oh, by the way, we should also save this here. Sorry, I forgot that before. So that's gonna be, I'll just call it lab 3 for now. What did we just talk about? So we wanted to write, so then we can here, we can import EMG functions as, let's just call it EMGF. And then we can use all the different functions that we put in this functions library. So first, what we said was that we wanted to remove the mean of this data. Let's have a look here again. So this means that we want to have almost like we want to have zero going through this data here. Okay. So for this, we're gonna write a new function now. We'll call it remove mean. You guys can call it whatever you want. I just like the remove mean. And for this, we really just need the EMG data, okay? And then I can already copy and paste the first part of what we found on the internet of scientifically sound. Let's put that in here. Boop. Okay, there we go. So we now need to add some libraries, so we can do that before the specific functions. Let's import numpy as np. Then we need to import, we got to copy and paste it from here. Import the plotting stuff, and then what else do we have here? Oh yeah, and we don't just want to send the EMG, we also want to send our time. There we go. So now we just wrote our own function here. One thing that I also like to do is I want to comment out the y limit, because this means that the y-axis can just go from minus 1.5, from minus 1.5 to plus 1.5. Our axis will be higher because our values are, I don't know, between 305 and 330 or whatever, which means we have values up to like 25 or so on. So we don't want to have minus 1.5 and plus 1.5. And here as well, let's comment this out as well. And now let's see if that will work. So if we want to call now this specific function, we can go back here, and now we can just say EMGF, that's how we call the library, EMGF.remove mean. And now we have to send the EMG data and the time. So maybe the easiest way is if we just define the EMG data here already. So let's say EMG equals, and this was weights.emg, and the time is weights.time, and that divided by 1,000 because our data is in milliseconds, right? So let's run this. And then we simply need to say EMG and time here. Let's run this here now. I need to first also run this here, and then see what happens here. There we go. So we went now from about 315 to around 0. So that already works. The next part now from the website, as we can see, is we want to filter our EMG signal. As I told you guys before, we want to filter out the frequencies that are higher than 450 hertz and lower than about 20 hertz. So I'm gonna copy and paste this part here as well. Put this in our function, and then we say a new function. Let's define this as EMG filter. It's important that this here is on a different indentation again, so it's more left again here. And then the input here, let's see, we'll load it later. And there we go. So also again here, this one needs to be more inside, that it knows it belongs into this function. And then we can actually, we don't have to put it here, we can put this here on top here so that it works for all the different functions that we're using it for. Okay, so let's see. It also needs, right. Right. Okay, so here it also needs the EMG correct mean now. So the correct mean is the data that we got from the function before, but we didn't actually use this here as an output. So what we want to do here is we want to say return, and then we want to say return EMG correct mean. Return correct mean. Save this. Then let's maybe also say, okay, we also need the SciPy here, the SciPy. Oh, we already have this. What's going on here? Oh yeah, okay, so as an input here, we'll have the EMG correct mean, which is the output from the function before. So that's the signal that is not offset anymore. And we also need to input the time. There we go, we can save this here. So what I forgot before, we now can add this, let's say correct. How is it called? Correct, it doesn't matter, it can be called anything, but I just like to have it the same name. EMG correct mean, EMG correct Okay, so let's run this here again. Now we also got the variable out here, EMG correct mean, and then our next step here will be, we will run, and you know what? We also want to have an output here afterwards. So our output here will be EMG filtered. So let's do it immediately. Let's say return EMG filtered. Oopsie. Save this here. And then we say here EMG filtered equals EMGF for our library again. And then we called the function, we called it EMG filter. And the inputs are the output from before, the EMG correct mean, and the time again. Let's run this. Oh yeah, there is one thing that we did before, but we forgot now, and this is that again, we have here the y-axis limits. So we also wanna comment out the y-axis limits here because our data is not between minus 1.5 and plus 1.5. So again, and there we go. So now we have actually like, and you can actually see that really, really well. So on the one hand, we have taken out all the frequencies that are under 20 hertz, which is like the slow frequency swinging here, which might be from the cables, it might be from some movements or whatever. So now here it's very beautifully straight, so we don't have very low frequencies anymore. And I think it's harder to see with the eye that we also removed some high frequency data. You can't see that one, but as said before, we actually changed, or we actually removed frequencies under 20 hertz and over 450 hertz. So let's see on our website now what the next steps will be after filtering the data. After filtering the data, we have to rectify the signal. So again, we can do the same as before. We can copy and paste the code. Let's go back in here. And then we say we create a new function again, and this function will be called, let's call it EMG rectify. Okay, copy and paste, change the indentation again. And then as an input, we need EMG filtered because that's what it's been used here. And we again also need the time. We can save it. And then as an output, we want to return the EMG rectified. EMG rectified. Isn't that fun? Okay, there we go. I hope that you guys are really learning here. What I really hope that you guys are learning is how helpful the internet can be if you find the right help there. So now I want to call EMG rectify, and we get a signal called rectify, EMG rectified. We call the library EMGF, and we call, wait, how do you spell it? Rectify F and F, okay. And as an input here, we want to use EMG filtered and the time. Let's see if that'll work. We forgot we forgot the axis again. Okay, let me see. The axis is here. 1 and 2. Save this, and now let's run it again here. There we go. So now you can see this here is the non-rectified data. It's around 0. So again, if you would use the mean here, it would just be like a straight line around 0. And then here we have the rectified signal. So now if you would take the mean, it would actually go up here, okay? That's so beautiful. This is where part 3 of the Scientifically Sound tutorial ends. And then you can click and go on to part 4. In part 4, they actually prepared a whole function for you that does all the things that we just did. What it doesn't do is remove the mean. So we still have to remove the mean before we send it into the function we'll talk about now. But then afterwards, the function from part 4 filters the data and rectifies the data. And then it also creates an envelope, which we'll talk about in a minute. So if you now copy and paste it, it's already the full function here. You can delete this part here because this part is how you actually call the function, and in their case, how to call it with different frequencies for the low pass filter, which we can also talk about later. But I want to give it a different name. Let's call it all together. All together. And here you can see what the first thing what they do is they filter the data as we did before. And you can also send the values for the filtering, so you can tell what should be the lowest value, which is 20 hertz, and what should be the highest value, 450. Then the second part is that they rectify the signal, and in the third part they create an envelope, which I want to explain now by just using it. So if we go back here, and now we say, see, what did just happen? Just clicked something on my, oh, there we go. That was all the steps that it did here. So let's say all together. And for all together, again, we need, where is it? All those things, right? So I'm just gonna copy it that I'll not forget. So we need the time, we need the EMG, whereas in our case, we need the EMG correct mean. EMG correct mean. Then we say for the low pass, we'll give it value of 10. Our sampling frequency was 1000, and so on. So the low pass filter, like this one, you'll see in a minute. EMG F. Okay, let's run this here. Oh, same mistake as before. We need to get rid of the while limits here. This one, and this one, and this one, and nope, and this one. Save it and try this again. There we go. So the focused region is actually also not very important for us. So there are a few more things that we can delete here, which is we don't need the last plot here. Let's maybe just comment it out here. And then maybe you saw it on the graph. I can see it anymore. It also, I'll show you. So if we take out the fourth part of the plot, then we just have to create a subplot that is just 3 different windows. So we have to change that everywhere. Hoppala, hoppala. 3, 3, 3, 3, and again 3, 3. Save this, check it out again, how it looks like. There we go, so now we just have 3. And then it also gives us a red line here, so for which focused region it actually used. So we can also delete everything that creates the red line, which is this one here. And I'm not sure if there was an, oh yeah, and this one here. We also don't need this here. And there we go, let's go again. There we go. So here we have our already without offset unrectified EMG data. Here we have our filtered and the rectified signal. And then here we have the envelope. So what the envelope basically does is that you can like actually look at the data and see better when the muscle was activated, how much it was actually activated. You filter you low pass filter the data again so that you can see better where it's going up and where it's going down. So if we now change our low pass filter here, and this is the number that changes this here. Let's say now 2, which will actually like show you the another version of this here. So let's say the frequency is 2 here. There we go. So now you see it even better. So what we do here now is we have a low pass filter, and now we can see better how the muscle was actually activated during this trial. And here we can also see very well that this one was a lighter weight, this one was kind of like a medium weight, and this was a heavier weight. Obviously, like you can play around with this number here, with this low pass number here, and figure out which one looks best and which one makes the most sense to judge the muscle activation with just by looking at it. And now we'll also look at how we can actually calculate the relative muscle activation compared to the maximum voluntary contraction that we also did before. One thing that I forgot to mention before is that we need 2 values from the altogether function that we also copied and pasted from the Scientifically Sound website. And those are, so we need to return them here. Those 2 are the EMG filtered one. So where do we have that? The EMG filtered one that we needed later for the frequency analysis. And then the other one is the envelope that we need for calculating the activation in the muscle. And this one, okay, save that. And we also need to say EMG filtered. Okay, now we have those 2 variables rectified and filtered here too. Now we have our data set prepared in a way that we can finally look at the relative muscle activation. So we have to do all the steps that we just did with the weights data, with the MBC data, and with the fatigue data. And then we can calculate the maximum contraction, so the maximum activity with the MBC from the MBC data. And from this, we can then calculate the relative muscle activation from the weights. And then we can also use the fatigue data to calculate the fatigue with the frequencies that we have in the data during the experiment. And we'll talk about this now.